So today's discussion we will be starting with another type of retrieval model, which is based on a linguistic model called language model. So those of you who had the NLP course, we had already discussed the concept of a language model, which is basically a probability distribution over a string of text. The ultimate outcome or ultimate target of using language model is to see or is to predict stochastically that how likely is the occurrence of a given string in a given language. For example, let's say there are four probabilities associated with four strings or four sentences. The first sentence is a quick brown dog. Second sentence is dog quick brown. Third sentence is un chin brun rapide. And the fourth is un brown dog rapide. Now, the target of a language model is to predict how likely this sentence is given a language model. This language model is given. This language model can be associated with, say, for example, let's consider the English language model. So the English language model states a probability distribution over a string of text where the sentence formation is defined by the English grammar, isn't it? So following the grammar, a sentence or the generation of a sentence can be actually predicted probabilistically. That is, given a language model associated with English, we can actually check how likely that the sentence will be generated from the English text. Okay. So from this sentence or from this set of sentences here that is containing four sentences here, we can understand that given the English language model, this is the most likely sentence to be generated. A quick brown dog. This will be the second most likely generated sentence. Dog quick brown. Why this is less than P1 is because it is not actually following the grammar. But still, the words are English words. So essentially, a language model prediction or language model, based on the language model, the occurrence probability, probability calculation consists of two parts. First part is basically the word overlap, and second part is basically the grammar, whether it is actually following the grammar or not. And as you can understand, this should be given higher priority, because if I write a Hindi or a non-English word here, that should be given less priority. Why? Because the chance of, let's say, if I put the word, say, Guten here. So a Guten quick brown dog. Let's say the sentence is like this. So if we consider an English language model, then there will be some probability associated with the occurrence of A. some with quick, some with brown, and some with dog. All of them are from the English vocabulary, right? But this term, guten, is actually a German term. So the probability of seeing this German term in an English vocabulary will be very less, say 0.001, less than very, I mean, it will be a very less value. Probability of seeing guten in English, given the English, so just probability of observing guten given the English language model. This will be very less. So as we can understand, the word should be given higher probability, higher weight here in this case, while computing the word occurrence, or to check whether a given string is actually an observation that can be drawn from a language model or not. So following that, this will be the highest probability. This should be P1 will be the highest, P2 will be the second highest. Now in P3 and P4, this term is actually a word, basically an English word. In this case, all of the four words are actually non-English words. So this should be the third highest, and this should be the fourth highest. Now, in information retrieval, we will be considering P1 and P2 as the same, because I hope you can understand the reason, because as I have discussed, as we have discussed, all of the things are, all of the retrieval models are basically bag of word model. In bag of word model, we are basically assuming term independence, and we are not actually considering the occurrence, the exact position of the occurrence. Although this is not actually entirely true, in case we are using a positional index based retrieval, in case of a positional index based retrieval, this can be actually considered separately. Positional index based retrieval, this can be considered. The term occurrence can also be, or the position at which the term occurrence is happening can also be considered. Okay, perfect. So in short, the probability retrieval, the language model is basically a model that assigns a probability to a sequence of sequence of words by means of probability distribution. So here the vocabulary of English is having one probability distribution. Now, given this four sentences, we can actually predict how likely this probability distribution is generating this sentence or this sentence. These are basically this P1, P2, P3, P4 here. Now, how this language modeling concept can be used for information retrieval, or particularly how this language modeling can be used for retrieving documents based on some keyword queries. To start with the discussion, I'll be discussing a very important and very interesting concept called noisy channel model. So, yes, you have any question?
Yes, sir. Sir, please go to the previous slide.
Yes.
Sir, this probability distribution graph, this is a probability distribution of the individual words or the phrases?
No, This is basically the probability distribution of the entire vocabulary of English.
Okay.
So you can understand that this is a huge, I mean, there will be huge number of points here. And there can be multiple. Actually, I should not be drawing a single distribution here. In English, there will be, I mean, in any language, there will be multiple distribution associated with multiple topics of the document or topics discussed in the vocabulary. So to keep things simple, I'm just, so given a vocabulary, we can basically consider a probability distribution associated with each of the topics that are discussed in the entire collection. In other words, what we can say is, thanks a lot that you asked this. Let me discuss this now. I'll be discussing this later as well. Let's say a document, I mean, we know that a document is basically a set of words, isn't it? Now, we know a document, so let's consider a news article. So the document is a news article. So the article or the document is basically discussing some topic, right? It can be a single topic, it can be multi-topical, right? Now, what we will be essentially doing is we will be creating a language model for the document as well. And we will be assuming that for each topic in the document, there can be multiple distributions associated with the different topics. But we actually don't know how many topics are there in the document. It can be a small document containing only one topic, which in the sense we can say a single topical. It can be a multi-topical document as well. For example, if we consider any Wikipedia article, so any Wikipedia article if you open, so let's say if you open the Wikipedia article on, say, I don't know, say Sachin Tendulkar, or let's say if you open the Wikipedia article on Ukraine, you will be finding multiple topics. One topic is associated with the independence of Ukraine from the Soviet Union. Other topics will be the geographic distribution or geographic situation of the country. There will be another topic discussing the culture, another topic discussing the, let's say, football. And of course, there will be another topic, which is the recent conflict between Ukraine and Russia. So essentially, a large document such as the Wikipedia, I mean, traditional general Wikipedia article, it will be multi-topical. But we actually don't know how many topics will be there in the document. So essentially, we consider a document having a single topic or having a single probability distribution, which is associated with the language model of the document. And here in this example, we are considering that the English following the word, basically following the grammar, there can be a single probability distribution associated with the English vocabulary. And we are computing how likely that probability distribution of vocabulary of English is generating this document, this sentence, or this sentence, and this sentence. Is it clear? Thanks a lot for asking this. I will be discussing this later. Yes, please.
Sir, I have another doubt. Sir, you said that
please.
Because we are considering a bag of words, so the order is not of very much importance. The P1 and P2, the probability is the same. So, sir,
Yeah,
if we do not use a positional indexing or something like that,
right.
then we may not able to be search the phrases, because the if this is a phrase, then
Very
it should
nice.
be together. Together, this all words should
Exactly,
organize together.
exactly. Thanks a lot for again, I mean, pointing out this. This is essentially one of the question in your mid-sem. So the question was, in order to search for phrases in a hash table, what shall we be doing? Can we simply use a hash table to store the index, store the inverted index? The answer is no. What we need to do is, number one, I guess everyone have answered this using stating that we need to store the position somehow so that we can have this positional indexing thing. Number two solution is, consider the words, let's say word 1 and word 2 are basically a phrase. Let's say Hong Kong. So rather than considering them as two different tokens, what we can do is we can consider them as a single token. So given in this case, given a query say Hong or a query say Kong, this will not be matching. So it will only be matching if we are giving both the phrase. So in case of IR, where we are actually considering the bag of words, this kind of a situation can actually be taken care of by considering them as single words. In that case, we will be basically Hong Kong and King Kong. As there is a Kong is matching, this can be a false match. That is, we are searching with Hong Kong and the document is containing the term King Kong. Then there is a single word query term matching in the document. So there will be some score that will be assigned to the document based on the occurrence of the single query term here. But what we can do is, as I said, either we can use a positional indexing, or we can actually store the phrases as a single entity. Is it clear now?
Yes, sir. But stored these phrases as single. Suppose if I stored a quick brown dog
Mm-hmm.
as a single entry, then if I search for a quick brown
Mm-hmm.
only, then we will not get any result.
Correct, absolutely correct. But the thing is, so you are storing a quick dog, right, as a phrase, right? Now, when your query is containing a quick dog, here again, this will be considered as a phrase. So here, now you have only two query terms or two term query. One is A, let's say for Q1, and another is quick dog, which is Q2, the second query term. So in that case, it will be basically matching, isn't it? Got it? I mean, the same
Yes, sir.
phrasing shall also be needed to be performed at the query end as well. Otherwise, the situation, I mean, as you are saying, if we are basically storing the phrases during the indexing and we are not actually considering the phrase while doing the query representation, then there will be no match. In that case, it will be basically quick one term and dog another term. In that case, there will be no match, isn't it? Got it?
Yeah, thank you.
Okay, great. So the noisy channel model of information retrieval. So in information retrieval, uh, what we do is we transform the information need into some keyword, and based on the keyword we perform the retrieval, isn't it? So what if this transformation is through a noisy channel? That is, let's say we have an information need from the information need, we are generating the query, and this channel, this transformation channel, is actually a noisy one. By noisy, I am saying that whatever I am providing here or whatever I have as the information need, I am not able to actually formulate its corresponding query. For example, let's say I am looking for the famous award which is given in India, which is called Shanti Swarup Bhattacharya Award. I hope most of you have heard the name, which is actually considered very prestigious and equivalent to the Nobel in India, in Indian science. So let's say I can't remember this thing, Shanti Swarup Bhattacharya. I can't actually remember. I have heard from someone, but I can't actually remember. So my information need is something like that. I want to actually understand or know who have won the Shanti Swarup Bhattacharya Award in say 2002 in say physics. So I can't actually remember the name of the award, but I know that it is a prestigious award in science in India equivalent to Nobel. So although my information need was based on this, I cannot actually formulate the corresponding query here correctly. So this is basically a noisy channel. So this noisy channel is actually cannot convert the information need into a proper query. So also there is another thing is which is highlighted here, prestigious. The more popular spelling is GIOUS, not GEOUS. So it is, you can consider a typo. Again, in my information need, I had, so information need is basically inside my mind. I do not actually, if I say prestigious, you will not be able to understand whether I know the exact, whether I know the correct spelling of the word prestigious or not. As I am saying prestigious. So it can be the case that while formulating the query from the information need, might be the case that I don't know actually what is the correct spelling of the word. So this is another form of noisy transformation. So after forming the query, after passing through this noisy channel, there can be other type of noisy channels as well. We will be looking or will be discussing them later on. But let's say after this transformation, we have transformed the information need into a query. Now the task of the information retrieval machine is to check or is to select all those documents which matches the keyword query. So the machine is not aware of this actual information need. Note that the relevance of the document will be considered based on the information need. Given the query, the documents that are being retrieved are considered to be relevant by the information retrieval machine, but they might not be the retrieval one, might not be the actual relevant one. The relevance can only be assessed or evaluated by the person who is actually having the information need. Let's say I have the information need that I want to know what is the reason behind the conflict between Ukraine and Russia. And let's say you also have the same information need, but I have some prior knowledge. I have the I mean, I know some history regarding the breaking of the Soviet Union, then the presence of NATO and its influence in this conflict and so on. But let's consider you don't know all those details. So you just out of nowhere you have read in the news that there is a conflict going on between Ukraine and Russia. You don't know about the history, so you just submitted a query like Ukraine, Russia conflict, and I also provided the same query. Now, if some documents are actually returning based on this query, this return query, which is basically discussing the history, I know the history. It might be the case that I want to know some more details regarding that. So a very general document will be non-relevant from my point of view, but it can be relevant from your point of view. So this relevance and non-relevance is actually dependent on the person who is having the information need. So again, recapping the thing, the documents will be, sorry, the documents will be judged based on the information need, but the retrieval will be performed based on the query, which is a transformed version of the information need. Is this concept clear? This is a very important, pillar in order to understand the information retrieval process. This concept of relevance, non-relevance, evaluation, and so on. So, retrieval based on language model is basically replicates this kind of a scenario. So, in information retrieval, a document will be considered as a good match to a query if the document model is likely to generate the query. That is, instead of earlier, you can say, you can see that from the information need, we are actually formulating the query, right? Or from the information retrieval model's point of view, it looks at the picture in this way. It considers that the user know the relevant documents, and from the relevant document he had chosen, or the person or the user had chosen some words as a query term. So it is basically the other way around. Earlier, here from the information need, we are generating the query, and based on the query, we are computing this matching. Here, we are considering that the user is aware of the relevant document, but he is actually looking for this one. He wants to choose this, he wants to read this. And this document is containing some terms, right? So he, in his mind, he had a very rough sketch of the relevant document or relevant documents. It can be multiple documents. So how he generates the query is basically he writes down the query words which are likely to appear in these documents. And so basically the query is generated based on a model like this. What is this? Probability of Q given the language model of the document T, where T is considered to be a relevant document. So this is called the document model or document language model. So what is this probability is saying? Probability of generation of Q query given the document's language model. So how likely that this document will be generating this query? So this is the whole idea that works behind the language model based retrieval models. So of course, this generation is the crucial part in formulating a retrieval model based on this LM. So coming up with a good query is an essential topic, essential thing, essential task. What we can do is we can use words that would likely to appear in the relevant documents as the query terms. So as I said here, we will be choosing certain words which are appearing, which should be appeared in the relevant document. We can choose these terms as the query terms. This is a very general way of choosing a good query. So this is actually happens in our mind. Now, as I said, LM based retrieval models actually replicates this thinking process. So what it does is basically it considers a document is a good match to a query if the document model is likely to generate the query. Similarly, earlier case happens if the document contains the query terms often. So a document, so a language, so an LM based retrieval model will be giving, so LM based retrieval model will be giving weight to a document D1 larger than a weight to a document D2 if the query terms are occurring more number of times in this document D1 than in D2. Then again, this more number of times, this rareness and all, those we have already discussed during the TF-IDF model or the BM25 will be taken care of during estimating this language model of the document. So the bottom line of this LM-based retrieval model is build a probabilistic language model MD for each of the document belonging to the collection. So if the collection is containing say 1000 documents, we will be basically creating 1000 language models associated with each of the documents, and then given a query, we will be checking what is the probability of generation of the query given some of the DIs. Essentially, we will be doing this for all the documents, and this probability, as you can understand, will be different for different documents, and based on the highest probability or based on the probability, we will be ranking the documents. The documents with highest probability will be ranked at the first position, then the second position, second rank, and so on. Now, this is actually called the document model or the document language model. This is also called document language model. Similarly, what we'll be doing is we'll be building a probabilistic language model for the query, and which will be basically considered as a query model or query language model, and we will be ranking the document based on the probability of document model generating the query model. Basically, probability of MQ given MD. Now note that this is a single one. For a given query, this will be a single one. So this will be unique for all the documents in the collection. So essentially, we also consider this. I mean, we can actually, I mean, we will be using the notation Q to denote the query language model here. So basically, this will be referred to, or this will be denoted as this. That is probability of generation of the query given the language model of the document. this will be the score of the document for the query, or of the document for the query Q. And this will be computed for all D belonging to the collection C. So we will be computing this value. Now, I hope you can correlate this with the discussion on inverted index. Essentially, if a collection is containing, say, 100 million document, we need not do this for all 100 million documents. We can only consider those documents which are containing the query terms using the inverted index. So essentially, although I have written for all documents belonging to C, it is basically, which is basically approximated as approximated as for all documents containing Q terms or query terms. So it's, I mean, considering this and considering this, it seemed a little bit impractical, because to consider all the documents, it's not actually, I mean, it's waste of time as well, because if the query term is not actually occurring in the document, as we have said, the bag of words model that we are doing, the bag of word model, there is no way the document will be considered as relevant for the query. So we will be only considering those documents containing the query terms.